The key factor in this situation is the definition and classification of the lighting system. Emergency lighting system, or ELS, as per National Electrical Code Section 517.2, is intended to illuminate escape routes and critical areas to facilitate safe egress during an emergency. It is typically required in areas where life and safety are at risk, such as hospitals, schools, and public buildings. A delayed connection equipment standby branch, or DCESB, circuit is used to power equipment that is not essential for immediate egress but may be needed after an emergency, such as lighting in non-critical areas. While HCFC is not explicitly prohibited in emergency lighting systems by the National Electrical Code, it is generally not recommended due to its flammability. The National Electrical Code requires that emergency lighting system wiring be installed in a manner that ensures its integrity during an emergency, typically involving rigid conduit or other protective measures. Many hospitals have additional guidelines beyond the National Electrical Code that restrict the use of HCFC in emergency lighting systems. This may be due to concerns about the potential for smoke and toxic fumes in the event of a fire. In this case, the lighting in a file room does not meet the definition of emergency lighting system since it is not essential for immediate egress. Therefore, it could be argued that the use of HCFC on the delayed connection equipment standby branch is acceptable, provided that it is installed in a safe and code-compliant manner. To ensure compliance and minimize safety risks, consider the following recommendations. Firstly, consult with the hospital's facility management team to confirm the guidelines on the use of HCFC in emergency systems. Secondly, install HCFC carefully, using bat wings to keep it off the ceiling and away from potential hazards. Thirdly, label the circuit clearly as delayed connection equipment standby branch to avoid confusion. And fourthly, consider exploring alternative wiring methods, such as surface-mounted conduit, that do not require breaking out the ceiling. It is important to understand the nuances between the National Electrical Code requirements and specific hospital guidelines when dealing with emergency lighting systems. Emergency lighting systems, or ELS, are designed to provide illumination in critical areas during power outages or other emergency situations. National Electrical Code Section 517.2 defines ELS as a system intended to supply illumination essential for safety of life and property, where a failure of the normal supply could create a hazard. This includes areas such as exit routes, operating rooms, and intensive care units. On the other hand, delayed connection equipment standby branch, or DCESB, circuits serve equipment that is not immediately necessary for life safety but supports essential operations after an emergency. This might include lighting in areas like file rooms, administrative offices, or non-critical storage spaces. The National Electrical Code does not explicitly prohibit the use of HCFC or hazardous condition flexible cable in emergency lighting systems, but it sets stringent requirements for the installation and integrity of emergency circuits. Section 700.9 addresses wiring for emergency circuits, stating that it must be designed and installed so that it is suitable for the conditions of use and must maintain its circuit integrity for the time duration that the emergency system is required to operate. This often implies using more robust wiring methods such as rigid metal conduit, electrical metallic tubing, or mineral insulated cable to protect against physical damage and fire. Hospitals often have additional regulations that go beyond the National Electrical Code. These regulations may restrict or prohibit the use of HCFC in emergency lighting systems due to concerns about flammability and the potential for toxic fumes during a fire. These concerns are particularly relevant in healthcare facilities where vulnerable patients are present. When considering the use of HCFC in a file room's lighting system connected to a delayed connection equipment standby branch, several factors should be taken into account. Firstly, determine whether the file room truly falls outside the definition of an area requiring emergency lighting as defined by National Electrical Code Section 517.2. If the file room is not essential for immediate egress or light safety, it might be permissible to use HCFC, provided that it complies with all other applicable codes and standards. Secondly, ensure that the HCFC is installed in a manner that minimizes risk. This includes using batwings to support the cable, keeping it away from heat sources and other potential hazards, and properly securing all connections. Thirdly, clearly label the circuit as a delayed connection equipment standby branch to prevent confusion during maintenance or future modifications. Fourthly, explore alternative wiring methods that offer greater protection and compliance. Surface-mounted conduit, for example, can provide a secure and code-compliant solution without requiring extensive demolition of the ceiling. Another option is to use cable tray systems, which can support multiple cables and provide easy access for future modifications. Finally, always consult with the hospital's facility management team and the authority having jurisdiction to ensure that the proposed installation meets all applicable requirements and guidelines. Obtaining written approval can help avoid potential conflicts and ensure that the installation is safe and compliant. In summary, while the National Electrical Code does not explicitly prohibit the use of HCFC in all emergency lighting systems, its use should be carefully considered based on the specific application, the potential risks, and any additional requirements imposed by the hospital or local authorities. Prioritizing safety and compliance is essential when working with emergency systems in healthcare facilities. Let's delve deeper into the technical aspects and considerations for using HCFC in a hospital setting, particularly in relation to emergency and standby power systems. Hazardous condition flexible cable, while not entirely forbidden by the National Electrical Code for emergency systems, warrants a cautious approach due to its construction and material properties. HCFC typically consists of insulated conductors enclosed in a flexible outer jacket. The flexibility, while advantageous for insulation in tight spaces, can also make it more susceptible to physical damage and degradation over time compared to rigid conduit systems. The primary concern with HCFC in emergency systems is its potential behavior in a fire. The outer jacket, often made of polyvinyl chloride or similar materials, can release toxic fumes when burned. These fumes can pose a significant hazard in a hospital environment, especially to patients with respiratory issues. Additionally, the insulation of the conductors may degrade rapidly under high heat, potentially leading to short circuits and failure of the emergency lighting system. National Electrical Code Section 700.9, as previously mentioned, emphasizes the need to maintain circuit integrity for emergency systems. This means that the wiring method must be able to withstand the expected environmental conditions, including exposure to heat, moisture, and physical stress, for the duration that the emergency system is required to operate. Rigid metal conduit, intermediate metal conduit, and electrical metallic tubing are generally preferred for emergency circuits because they provide superior physical protection and fire resistance compared to HCFC. These conduit systems can help contain a fire within the raceway and prevent the spread of flames and smoke. Furthermore, they offer excellent protection against mechanical damage, ensuring the reliability of the emergency circuit. When evaluating the suitability of HCFC for a delayed connection equipment standby branch circuit in a file room, it's crucial to consider the specific characteristics of the space and the potential risks. Is the file room located in an area with a high fire risk? Are there any sensitive electronic equipment or materials stored in the room that could be damaged by smoke or fumes? Are there any specific requirements or restrictions imposed by the hospital's insurance carrier or accreditation body? These are all important questions to address. If the file room is deemed to be a low-risk area, and the use of HCFC is permitted by the hospital and local authorities, it's essential to follow best practices for installation. Firstly, select HCFC that is specifically listed for the intended application and voltage rating. Secondly, ensure that the cable is properly supported using batwings or other approved methods to prevent sagging and strain. Thirdly, avoid running the cable through areas where it could be exposed to physical damage or excessive heat. Fourthly, use appropriate connectors and fittings to ensure a secure and reliable connection. Fifthly, clearly label the circuit as a delayed connection equipment standby branch to prevent confusion during maintenance or future modifications. In addition to these installation practices, consider implementing additional safety measures, such as installing smoke detectors in the file room and connecting them to the hospital's fire alarm system. This can provide early warning of a fire and allow for prompt evacuation. Furthermore, consider using fire-rated cable ties and supports to help contain the spread of flames in the event of a fire. It's also worth exploring alternative wiring methods that offer a balance of flexibility and protection. For example, armored cable, or AC, provides a higher level of physical protection than HCFC while still allowing for some degree of flexibility. AC consists of insulated conductors wrapped in a flexible metal sheath, which helps protect against damage and fire. Another option is to use liquid-type flexible metal conduit, or LFMC, which provides a watertight seal and protects against corrosion. LFMC can be used in conjunction with standard conduit fittings to create a flexible and durable wiring system. When making a decision about the wiring method for the file room's lighting system, it's important to weigh the costs and benefits of each option. While HCFC may be the least expensive option upfront, it may not provide the same level of protection and reliability as other wiring methods. Investing in a more robust wiring system can help reduce the risk of fire and electrical failures, which can ultimately save money in the long run. Furthermore, it's important to consider the long-term maintenance costs associated with each wiring method. HCFC may require more frequent inspection and replacement than conduit systems, especially in areas where it is exposed to physical damage or environmental stress. In conclusion, the decision to use HCFC in a hospital's emergency or standby power system should be made carefully, taking into account the specific application, the potential risks, and all applicable codes and standards. Prioritizing safety and compliance is essential when working with electrical systems in healthcare facilities, where the well-being of patients and staff is paramount. Consider the implications of the National Electrical Code requirements for emergency systems in hospitals, specifically in relation to the use of HCFC. The National Electrical Code, in Article 517, addresses healthcare facilities and provides specific requirements for electrical systems in these environments. These requirements are designed to ensure the safety and reliability of electrical power, especially during emergencies. Section 517.30, for example, covers essential electrical systems and outlines the different types of systems required in hospitals, including emergency systems, equipment systems, and critical branch systems. As previously discussed, emergency systems are intended to provide power to life safety equipment such as exit lighting, fire alarms, and critical care areas. Equipment systems serve equipment that is essential for patient care but not directly related to life safety, such as operating room lights and X-ray machines. Critical branch systems supply power to equipment that is necessary for the orderly shutdown of operations during an emergency, such as ventilation systems and data processing equipment. The National Electrical Code requires that emergency systems be designed and installed to operate independently of the normal power supply. This means that they must have their own dedicated power source, such as a generator or battery system, and must be able to automatically switch over to the emergency power source within a specified time period, typically 10 seconds. Section 700.12 provides detailed requirements for emergency power sources, including their capacity, reliability, and maintenance. The National Electrical Code also sets requirements for the wiring of emergency systems. Section 700.9 states that emergency wiring must be physically separated from other wiring systems to minimize the risk of damage or interference. This can be achieved by using separate raceways, cable trays, or cable routing pathways. In addition, emergency wiring must be protected against fire and physical damage. This can be accomplished by using fire-rated cable or conduit and by installing the wiring in areas that are not subject to mechanical stress or environmental hazards. When considering the use of HCFC in a hospital's emergency system, it's important to evaluate whether it meets the requirements of the National Electrical Code and any applicable local codes or standards. As previously discussed, HCFC may not be suitable for use in emergency systems due to its flammability and potential to release toxic fumes during a fire. However, if the authority having jurisdiction approves the use of HCFC in a specific application, it's essential to follow all applicable installation requirements and best practices. This includes using approved connectors and fittings supporting the cable properly and labeling the circuit clearly. It's also important to consider the potential impact of the National Electrical Code's arc fault circuit interrupter, or FSI, requirements on emergency systems. FSIs are designed to detect and interrupt electrical arcs, which can be a leading cause of fires. The National Electrical Code requires FSIs in many branch circuits in residential and commercial buildings, including those that serve lighting and receptacle outlets. While FSIs can help prevent fires, they can also be prone to nuisance tripping, which can disrupt the operation of emergency systems. Therefore, it's important to carefully select and install FSIs in emergency circuits to minimize the risk of nuisance tripping. One way to reduce the risk of nuisance tripping is to use FSIs that are specifically designed for use in emergency systems. These FSIs are typically more tolerant of transient voltage spikes and other electrical disturbances that can cause false trips. Another way to reduce the risk of nuisance tripping is to install surge protection devices, or SPDs, on the emergency power system. SPD can help protect against voltage surges caused by lightning strikes or other electrical events which can trigger FSIs. In addition to the National Electrical Code, hospitals may also be subject to requirements from other organizations, such as the Joint Commission. The Joint Commission is an independent organization that accredits and certifies healthcare organizations in the United States. The Joint Commission has standards for electrical safety that are designed to ensure the safety of patients, staff, and visitors. These standards may include requirements for emergency power systems, electrical equipment maintenance, and electrical safety training. To ensure compliance with all applicable codes and standards, it's important to work with a qualified electrical contractor who has experience in healthcare facilities. A qualified contractor can help you design and install an electrical system that meets all the necessary requirements and provides reliable power during emergencies. Remember, the primary goal of electrical safety in hospitals is to protect patients and staff from harm. By following the National Electrical Code and other applicable codes and standards, you can help create a safe and reliable electrical environment in your healthcare facility. Let's explore the practical aspects of installing HCFC in a file room connected to a delayed connection equipment standby branch, while emphasizing safety and compliance with the National Electrical Code and hospital regulations. Firstly, before commencing any electrical work, it is crucial to conduct a thorough site assessment. This involves inspecting the physical layout of the file room, identifying potential hazards, and reviewing the existing electrical infrastructure. Pay close attention to the type of ceiling, the presence of ducts, pipes, and other obstructions, and the availability of access points for running cables. Also, verify the voltage and current requirements of the lighting fixtures to ensure that the HCFC is properly sized and rated. Secondly, obtain all necessary permits and approvals from the local building department and the hospital's facility management team. This step is essential to ensure that the installation complies with all applicable codes and regulations. Provide detailed drawings and specifications for the proposed installation, including the type of HCFC to be used, the routing of the cables, and the location of all connections and terminations. Thirdly, select HCFC that is specifically listed for the intended application and voltage rating. Ensure that the cable is suitable for use in a dry location and that it is rated for the appropriate temperature range. Choose HCFC that is flexible and easy to work with, but also durable enough to withstand the expected environmental conditions. Fourthly, plan the cable routing carefully to minimize the risk of damage or interference. Avoid running the cable through areas where it could be exposed to physical stress, moisture, or heat. Use batwings or other approved supports to secure the cable to the ceiling and keep it away from ducts, pipes, and other obstructions. Maintain a safe distance from sources of electromagnetic interference, such as transformers and electrical panels. Fifthly, use appropriate connectors and fittings to ensure secure and reliable connection. Use connectors that are specifically designed for use with HCFC and that are listed for the intended application. Tighten all connections to the manufacturer's specifications to prevent loose connections and overheating. Sixthly, follow proper grounding and bonding procedures to minimize the risk of electrical shock. Connect the equipment grounding conductor of the HCFC to the building's grounding system. Use bonding jumpers to connect metal enclosures and other conductive parts to the grounding system. Seventhly, test the installation thoroughly before energizing the circuit. Use a multimeter to verify that the voltage and current levels are within the specified limits. Use an insulation resistance tester to check for any leakage current. Use a ground fault circuit interrupter or GFCI tester to verify that the GFCI protection is working properly. Eighthly, label the circuit clearly as a delayed connection equipment standby branch to prevent confusion during maintenance or future modifications. Use a permanent marker or label maker to create a clear and legible label. Include the circuit number, the voltage, and the amperage rating. Ninthly, provide training to hospital staff on the proper operation and maintenance of the emergency lighting system. Explain the purpose of the system, the location of the emergency power source, and the procedures for testing and inspecting the system. Provide a written manual that includes all relevant information. Tenthly, conduct regular inspections and maintenance to ensure that the emergency lighting system is operating properly. Inspect the HCFC for any signs of damage or deterioration. Test the emergency power source to verify that it is capable of supplying power to the lighting fixtures for the required duration. Replace any faulty components promptly. In addition to these practical steps, it's important to be aware of the potential hazards associated with working with electricity. Always disconnect the power before working on any electrical circuit. Use insulated tools and equipment to protect yourself from electrical shock. Wear appropriate personal protective equipment, such as safety glasses and gloves. Work with a partner to provide assistance in case of an emergency. By following these safety precautions and best practices, you can help ensure that the installation of HCFC in a file room connected to a delayed connection equipment standby branch is done safely and in compliance with all applicable codes and regulations.